All right, welcome back to the deep dive. We're back with another episode, deep dive. And this time, we're going to be talking about something that is absolutely critical for anybody who works with AIX, and that's performance tuning.
Right. You want to make sure your systems are running at their best. And so this deep dive, that's our mission here today, is to give you the insights, the understanding of all those key tools, all the concepts that matter, so you can look under the hood and know exactly what's going on and make your system sing.
Exactly. And we've been digging through a ton of IBM documentation, all those like really dense manuals on AIX performance tools, but we're going to like distill all that down, make it practical for you so you can actually use this stuff.
Yeah, this is not just some theoretical stuff. This is about giving you like the hands-on tools and techniques that you can apply today and actually make a difference in your AIX environments.
So think of it as like, you're getting those aha moments where you suddenly understand like, oh, that's how that metric actually works.
Right.
And then you can actually use that to improve your system. So where do we even begin when we're talking about AIX performance? Like what are we really trying to achieve?
Well, one of the key concepts to understand is this idea of the next bottleneck.
Right.
Right? So you might spend all this time and effort optimizing one particular area, like say your CPU utilization.
Right. Get it really nice and low.
But then you realize that, oh, wait a minute, the performance is actually now being limited by something else entirely, like maybe disk I/O or memory. It's sort of like, you fix one thing and then another issue pops up.
Yeah, it's like whack-a-mole.
Exactly.
Okay, so we got to be aware of these like cascading bottlenecks, basically. All right. So what tools does AIX give us to help us like see these bottlenecks?
Well, we've got a bunch of really great performance monitoring tools at our disposal. One of those fundamental ones is vmstat. Vmstat, it gives you this great high-level snapshot of what's happening in your system in terms of CPU activity, memory usage, and paging.
Okay, vmstat. I've used vmstat. I've definitely seen it. Sometimes it's a bit much, a bit cryptic, all those numbers flying by. What are the key columns that we should be looking at if we want to just get a quick sense of how the system's doing?
All right, so for like a really quick checkup, I tend to focus on a few key columns. So we've got RR that tells us how many processes are runnable. They're just waiting for their turn on the CPU.
Okay, so if R is high, that's a bad sign, right?
If R is consistently high, it usually means that your CPU is saturated. You don't have enough CPU cycles to go around. Then we've got B. That tells us how many processes are blocked, usually waiting for I/O to complete. And then there are the Pi and Po columns. Those show us how many pages are being paged in and out of memory. If those numbers are really high, it could be a sign that you're having some serious memory pressure and your system's spending way too much time swapping.
Oh, so that's the dreaded thrashing we hear about, right?
Yeah, exactly. Thrashing. And then, of course, we've got the CPU breakdown. You've got your US, your C, your WA, and your ID. Those tell you how much CPU time is being spent in user mode, system mode, waiting for I/O, and just being idle. If you see a really high WA, that's usually a pretty good indicator that you have a disk I/O bottleneck. Your CPU is just sitting there, twiddling its thumbs, waiting for the disks to catch up.
Okay, that's a good set of things to keep an eye on. Now, what about some of those other columns like avum and free? I know those are related to memory, but what do they actually tell us?
Right. So AVM, that stands for active virtual memory. Basically, it's a measure of how much virtual memory has been accessed recently.
Yeah.
And free, that's the size of the free list. That tells you how much memory is currently available for allocation.
So should avum always be lower than our total RAM?
Ideally, yes. If AVM starts creeping up way higher than your RAM, it probably means that you're dipping into your paging space a lot. And that's going to slow things down because disk access is much slower than RAM access. On the other hand, if AVM is way lower than your RAM, it might mean that a big chunk of your RAM is being used for file caching, like persistent and client pages.
Okay, so that's not necessarily bad, but it might be something to look into if we're trying to optimize memory usage for specific applications.
Right.
Now, I know we can run vmstat continuously to get like a live view of what's happening. How do we do that?
Yeah, to run vmstat continuously, you just add an interval after the command, like vmstat5, for example. That'll give you a new set of stats every 5 seconds.
Perfect. So we can watch those numbers tick by and see how things are trending. Now, what if vmstat is showing us that high WAR, indicating a potential disk I/O bottleneck? Where do we turn to dig deeper into that?
If we start seeing those signs of an I/O bottleneck, our next stop is usually IOstat. IOstat is our dedicated tool for getting those nitty-gritty details on disk I/O activity.
Okay, so it's like vmstat, but specifically for I/O. What kind of information does it give us beyond what we see in vmstat?
So the first report that IOStat gives you, that shows you like all the activity that's happened since the last time the system was booted or those counters were reset. But if you run it with an interval, like we did with vmstat, IOStat 5, then the reports after that, they show you just the activity that happened during that specific time interval, that 5-second window in this case.
Oh, that's handy, especially if we're trying to track down like transient spikes in I/O activity during peak loads or when certain applications are running.
Exactly. It gives you that really granular time-sensitive view.
All right, we'll definitely come back to IOStat and how to interpret its output when we focus on I/O performance later. So we've got vmstat for a system-wide overview and IOStat for detailed disk I/O. What other tools should we have in our AIX performance arsenal? I've also heard a lot about topas and nmon. What are those all about?
Oh, topas. Topas is fantastic.
Yeah.
It's like this really cool full-screen real-time system monitor.
Yeah.
And it gives you all this dynamic information, all these visualizations for CPU, memory, disk, network, you name it. It's very interactive, so you can easily drill down into different areas. And if you're working in a virtualized environment, then topas-c becomes your best friend.
Topas-c. What's so special about that version for virtualized setups?
Well, topas-c, it's specifically for monitoring the central electronics complex. That's what CC stands for. So in systems that have multiple LPARs, logical partitions, topas-c gives you this consolidated view of all the resource utilization across the entire physical server.
Oh, I see. So I can see how much CPU and memory each individual LPR is using, as well as the overall host level stats. That sounds super useful for understanding resource allocation and contention in a virtualized environment.
Absolutely. It's a must-have if you're managing AIX LPRs. You'll see each partition broken down. You see the memory usage in gigabytes. You can see how much memory is monitored, how much is in use, how much is available, all the details. Same with processors. You can see how many are monitored, available, how many are dedicated, how much of the entitled capacity is being used.
Wow, that's a lot of information. What about the host itself? Does topas-c show us any host level data?
Oh, yeah, definitely. It gives you the overall memory usage for the host, like the total memory and how much of it is being used. It also tells you how many logical partitions are running and gives you the aggregated CPU utilization for the entire host, broken down into user, system, weight, and idle percentages. And there's more. You get details on the physical memory, the entitled capacity, the virtual CPUs, and even stuff like voluntary context switches and the physical input-output activity for the entire host.
That's pretty comprehensive. Are there any limitations to topas-c that we should be aware of?
Well, one thing to keep in mind is that topas-c relies on broadcast queries, specifically the copas-query command, to discover and collect data from remote LPARs. And these broadcasts are usually limited to the same subnet.
Oh, so if I'm trying to monitor LPRs that are on a different subnet, I might run into problems.
Right, you might not see all the LPRs,
Mm-hmm.
but there's a workaround. You can manually add entries to the rsi.hosts file on the system where you're running topas-c.
Ah, so we can tell topas-c where to look for those remote LPRs. That's good to know. Now, what about capturing all this real-time performance data for later analysis? I know Topas has a recording feature, right?
It does. That's topasrec. It's a command line tool, and it lets you record all that beautiful data that Topas is displaying so you can analyze it later. You can even choose the format, Topas' own binary format or the more universally compatible nmon format.
Nice. Options are always good. And what kind of control do we have over the recording process?
Quite a bit, actually. You can set how long the recording should run for, how often data samples should be taken, how many days of data to keep in each file, how long to keep those files around, and you can specify the directory where those recorded files should be stored.
So we can customize it based on how much data we need and for how long we need to keep it. Can we also be selective about what metrics get recorded? Like if I'm only interested in disk performance, can I just capture those stats?
Absolutely. You can absolutely choose which specific metrics you want to include in the recording. So yeah, if you only care about disk stuff, you can focus on that. You can even drill down and capture those really detailed disk statistics or information on service times if you need to.
That's really flexible. So we've got Topas for that immediate real-time view, topas-c for a CEC-wide view in those virtualized environments, and topasrec to capture all that juicy data for later analysis. Now, what about SAR? I know that's another really popular performance monitoring tool, especially in the UNIX world. What role does it play in AIX?
Yeah, so it stands for System Activity Reporter. And it's a very powerful command line tool. Basically, it lets you collect, report, and save historical system activity data.
So it's like a historical version of vmstat and IOStat combined with the ability to save those reports for later review.
Yeah, that's a good way to think about it. For example, if you run SARU, it'll give you a report on microprocessor utilization. You'll see the breakdown of CPU time spent in user mode, system mode, waiting for I/O, and just idling. It also shows you how much physical CPU is being consumed and the percentage of the entitled capacity that's being used.
So in a way, it's giving us some of the same core CPU information that we'd see in vmstat and iostat, but from a historical perspective.
Exactly.
That's good to know. Sometimes having those different perspectives can be really helpful. All right, now that we have a decent understanding of some of these key performance monitoring tools in AIX, let's start digging a little deeper into specific areas, starting with CPU performance. What are some of the fundamental things we need to understand about how the CPU works in AIX, especially in relation to performance?
When we talk about CPU performance, one of the first things to understand is the difference between user mode and kernel mode. So user mode, that's where your applications run, along with most of the libraries they use. And then there's kernel mode. That's where the operating system itself is running. The kernel handles all the system calls from applications and deals with all the hardware interrupts.
So when we see those CPU utilization figures in tools like vmstat, iostat, and SAR, they're reflecting the time spent in both user mode and kernel mode.
Exactly.
Okay, so if I see a really high percentage of user time, it probably means that one or more of my applications is really hammering the CPU. And if I see a high percentage of system time, it might mean that the operating system itself is doing a lot of work, maybe handling a ton of system calls or interrupts. Now, what about this concept of processor affinity? I've heard that term thrown around a lot in the context of performance. What does that actually mean?
So processor affinity, that's basically the AIX dispatcher's tendency to try to keep a thread running on the same processor it was running on before.
Oh, so it tries to stick with the same CPU as much as possible. Why is that?
Because of something called the processor cache.
Yeah.
Each CPU has its own little bit of really fast memory called a cache, and it stores frequently accessed data and instructions there. So if a thread keeps running on the same CPU, there's a good chance that the data and instructions it needs will already be in the cache. And that makes things much faster because accessing the cache is way faster than going all the way back to main memory.
That makes sense. But I imagine there's got to be a trade-off somewhere. What if that CPU that the thread wants to stick to is busy?
Right, there's definitely a trade-off. If a thread has to wait too long for its preferred CPU to become available, it might actually be faster to just run it on a different CPU, even if that means having to fetch data and instructions from main memory. So it's a balancing act between those potential cache hits and the potential waiting time.
Okay, so it's not always a good idea to force a thread to stick to a particular CPU. Now, when we start talking about multiprocessor systems, things get even more complicated, right? I mean, managing CPU resources across multiple processors must be a whole other challenge.
It definitely adds another layer of complexity. While having more processors can obviously increase your overall system throughput, it also comes with its own set of overheads.
Such as?
Well, for one thing, the processors need to synchronize with each other, which takes time. And then there's the increased likelihood of cache misses, because now data might be spread across multiple caches. And then, of course, the operating system itself has to work harder to manage all those processors. It has to deal with things like locks and shared resources, which can add overhead.
Right, so just throwing more CPUs at a performance problem isn't always the solution. We have to make sure our workloads can actually take advantage of all that extra processing power. And that brings us to this idea of scalability, right? How well workload performs when you give it more processors.
Exactly. Scalability is often measured by looking at how much performance improvement you get when you add more processors. Ideally, if you double the number of processors, you'd want to see your performance double as well.
Right, but you're saying that rarely happens in the real world.
Rarely. You rarely see that perfect linear scaling because of all those overheads we talked about. In fact, sometimes you might even see a slight performance decrease when you go from a single processor system to a two-way SMP system, especially under very light workloads.
That's counterintuitive. So more processors don't always equal better performance. All right, now, if we want to drill down and get a more detailed view of CPU utilization, maybe at the process level or even the thread level, what tools can we use?
So if you want to see what's going on at the thread level, the panis command has got you covered. Specifically, you can use ttfio's elmo thread. This will show you information about every single thread running on the system.
Okay, and what should we be looking for in the output?
There's a column called CP, which stands for recent CPU usage. This value shows you how much CPU time each thread has been using.
So if I see a thread with a really high CP value, it means that thread is hogging the CPU.
Pretty much. But there's a catch. The CP value maxes out at 120.
Oh, so even if a thread is using more than 120 units of CPU time, it'll still only show 120 in the output.
Right. And another thing to remember is that for multi-threaded processes, the CP value that you see for the main process is actually the sum of the CP values of all its threads.
So if I see a process with a high CP value, I might need to dig deeper and use paste Elmo thread to see which specific threads are the real CPU hogs. Now, what if we identify a process or thread that's just using way too much CPU? Can we do anything to lower its priority or something?
Yeah, you can use the renice command to change the scheduling priority of a running process.
How does that work?
Every process has a nice value. A lower nice value means a higher priority. So if you increase the nice value of a process, you're basically telling the scheduler to give it less CPU time.
Okay, so we can use renice to manually adjust the priority of a process. But AIX also has some built-in mechanisms for dynamically adjusting process priorities, right? Like based on how much CPU a process is actually using.
It does. AIX has this algorithm that calculates what's called a CPU penalty for each thread. And this penalty is based on how much CPU the thread has been using recently and how many other threads are waiting to run.
So if a thread is using a lot of CPU, it gets penalized.
Exactly. And the penalty basically reduces the thread's priority, making it less likely to get scheduled. And there's also a decay factor that comes into play. The recent CPU usage of a thread gradually decreases over time if it's not actively using the CPU.
So even if a thread was a CPU hog in the past, it can redeem itself if it starts behaving better.
Right. And you know what's cool? You can actually tweak some of these scheduling parameters using the Skedo command. There's Skedo-NS or Skedo-D, which let you control things like the decay factor and how the run queue length influences priority.
Oh, so we can fine-tune the scheduling behavior if we need to.
Exactly.
That's pretty powerful. It seems like effective CPU performance analysis and tuning really involves understanding how the scheduler works and using the right tools to monitor and adjust things. All right, let's shift gears now and talk about another crucial piece of the performance puzzle, memory management.
When we dive into memory performance, two of the most important concepts are the translation look-aside buffer, or TLB, and the CPU caches. So the TLB, it's a tiny little cache that stores recent translations between virtual memory addresses and physical memory addresses.
Okay, so when a program tries to access a memory location, the system first checks the TLB to see if it knows the physical address for that virtual address.
Exactly. And if the translation is found in the TLB, that's called a TLB hit. And those hits are super fast because the TLB is extremely fast memory. But if the translation is not found, that's a TLB miss, and then the system has to do this whole page table walk to find the physical address, which takes a lot more time.
So TLB misses can really slow things down because they introduce all these extra lookups.
Absolutely. And the CPU caches, they also play a role here because they help reduce the need to access main memory, which is relatively slow compared to the caches.
Right. I know CPUs have these multiple levels of caches, and they try to keep the most frequently used data and instructions in those caches. So if a CPU can find what it needs in the cache, that's a cache hit, and it's really fast. But if it's not in the cache, that's a cache miss, and it has to go all the way to RAM, which is slower.
Right. And each level of cache is larger and slower than the one before it. So the fastest, smallest cache, the L1 cache, and the L2 cache, which is bigger and slower, and so on.
And the goal is to maximize cache hits at those higher levels, the faster levels, to minimize those trips to RAM.
Exactly.
Now, when we're looking at memory usage in vmstat, what are some of the key things we should be watching for? I know we talked about AVM before, that active virtual memory, and you mentioned comparing it to the total RAM. Can you explain a bit more about what that comparison tells us?
Right, so AVM gives you an idea of how much virtual memory is actively being used by processes. In a perfect world, your AVM would be less than your physical RAM.
Makes sense. So if AVM is way higher than RAM, it probably means we're hitting the paging space pretty hard, and that's bad for performance.
Yeah, exactly. It means you're swapping a lot, and swapping is slow. On the other hand, if AVM is way lower than your RAM, it could mean that a big chunk of your RAM is being used for caching file data, things like persistent and client pages.
Okay, so again, that's not necessarily bad, but it's something to be aware of if we're trying to optimize memory usage for specific applications. Are there any other memory-related columns in vmstat that we should be watching?
Yeah, definitely. Besides AVM and free, you've also got pin, which shows how much memory is pinned in RAM, meaning it can't be paged out. And then the in-use memory is broken down into working segment pages. Those are for memory used by applications. Persistent segment pages, those are mostly file system cache. client segment pages. Those are used for things like NFS, network file systems. And then at the end of the memory section, you've got the PGSP section, which tells you about your paging space.
Okay, PGSP, paging space. What do those numbers tell us?
It shows you the total amount of paging space you've got configured and how much of it is actually being used. Usually the total in-use memory is going to be bigger than the in-use paging space because the memory used for file caching doesn't get released right away when an application ends. But the paging space that's allocated to a process, that usually gets freed up as soon as the process exits.
Oh, I see. So there's a difference there between file cache, which can stick around even after an application is gone, and process memory, which gets released more quickly. Now, I remember you mentioned a special flag for vmstat that gives us some overall system memory statistic.
You're talking about vmstat and ISS.
Yeah, vmstat and ISS. What kind of information does that give us?
vmstat and ISS, it gives you a summary of all these different system events and memory-related counts. Like, it'll tell you how many page-ins and page-outs have happened. This can be really useful for understanding how your file system operations are impacting memory usage.
Can you give me an example?
Sure. Let's say you copy a huge file that hasn't been accessed recently. That's going to trigger a lot of page-ins as the system reads data from the file into memory. And you'll see that spike in the vmstat and ISS output.
So vmstat and ISS can give us a bigger picture view of memory activity beyond just that real-time snapshot that we get from regular vmstat. All right, let's talk a bit about some of the tunable parameters that can affect memory performance. I know we touched on the repg parameter earlier. Can you remind me what that one does?
Right, so repg, that's a tunable parameter that's part of AIX's memory load control mechanism. Basically, it sets a threshold, and when the system's memory usage hits that threshold, it triggers a more aggressive page stealing process.
Okay, and page stealing means the system starts taking memory away from processes that aren't using it actively and giving it to processes that need it more urgently.
Exactly.
So if repg is set to a lower value, it means the system will start stealing pages more aggressively.
Right.
But I thought you said the default value for repg is usually 0, which effectively disables this more aggressive load control. Why is that?
Well, on modern systems with a decent amount of RAM, the default memory management algorithms are usually pretty good at handling things. They don't need that extra level of aggressiveness. But in some specific cases, like if you're running old terminal emulators with really short timeouts, or if you're using the rounds command to test memory requirements under load, you might consider disabling the default memory load control by setting repg to 0.
Interesting. So it's a parameter that's less commonly adjusted on modern systems, but might still be relevant in those niche cases. Okay, let's move on to the topic of paging space. What are some of the key things we need to consider when we're configuring and managing paging space in AIX?
Paging space is crucial. It's what your system uses when it runs out of physical RAM, so you definitely want to make sure you've got enough of it.
How much is enough?
A good rule of thumb is to have at least as much paging space as you have RAM. And depending on your workloads, you might even need more. AIX also has this feature called early page space allocation.
Early page space allocation? What's that?
It's a way to make sure that you don't run into those dreaded out-of-paging space errors at the worst possible time. Normally, the system only allocates paging space when it's actually needed, when it's about to page something out to disk. But with early allocation enabled, it tries to allocate the necessary paging space up front when a process requests virtual memory.
Oh, that makes sense. It's like being proactive instead of reactive. How do we enable early page space allocation?
You can set the SALIC environment variable to early.
Okay, SALIC early. Got it. Anything else we need to be aware of with early allocation?
Yeah, there's this other environment variable called noDisclaim.
noDisclaim. What does that do?
Well, by default, when you have early allocation enabled, every time an application calls the free function, the system might do a disclaim system call. And those disclaim calls can eat up some CPU cycles.
Oh, I see. So setting noDisclaim true can help reduce that overhead.
Right. But it might also slightly delay when the paging space actually gets freed up, so it's a bit of a trade-off.
Right, something to keep in mind. Now, what about that nsysert tunable that you mentioned earlier? What does that one control?
Right, so nsysert, it's a VMM tunable, so it affects how the virtual memory manager behaves. Specifically, it changes what happens when an LPAR runs out of paging space.
Okay, and what's the default behavior?
By default, when the system runs out of paging space, it starts sending these sig danger signals to processes. And it might even start killing processes to try and reclaim some paging space.
So it's like a last-ditch effort to prevent the entire system from crashing.
Yeah, pretty much.
Yeah.
But if you enable nsysert by setting it to 1, the LPR will fail more abruptly when it runs out of paging space. It won't bother with those danger signals or trying to kill processes.
So it's like a faster, cleaner failure.
Right. And in some virtualized environments, that might actually be the preferred behavior.
Okay, makes sense. Now, I think there's also a VMM tunable called Scrub that's related to paging space. What does that one do?
Yeah, Scrub, that's another interesting one. It controls whether or not the system will try to free up paging space blocks that are associated with memory pages that were allocated using a deferred allocation policy.
Deferred allocation, what's that?
It's a way of allocating paging space only when it's absolutely needed.
Okay, so if Scrub is enabled, the system will periodically scan those deferred allocation blocks and try to free them up.
Exactly. And this can help reclaim some paging space over time.
That's cool. All right, let's talk a bit about page sizes. I know AIX supports different page sizes. What impact does the choice of page size have on memory performance?
Right, so AIX lets you use different page sizes for different parts of a process's memory. Like the data segment, the stack, the code, the shared memory.
And why would we want to use different page sizes?
Well, using larger page sizes can sometimes improve performance. It has to do with the TLB, the translation look-aside buffer we talked about earlier. Remember how TLB misses can slow things down? Well, if you use larger page sizes, each TLB entry can map a bigger chunk of memory, which means you'll have fewer TLB misses.
Oh, I see. So bigger pages, fewer TLB misses, better performance.
In theory, yes. But there's some potential downsides, too.
Like what?
Well, for one thing, larger pages can sometimes lead to more internal memory fragmentation.
Memory fragmentation, what does that mean?
It means that you end up with these little gaps of unused memory scattered throughout your RAM.
Oh, so even though you might have plenty of free memory overall, you might not have enough contiguous blocks of memory to satisfy a large allocation request.
Exactly.
That's not good. And you're saying larger pages can exacerbate this problem?
They can, yeah.
Yeah.
And another potential issue with larger pages is that they can affect thread creation in multi-threaded applications.
How so?
It has to do with stack guard pages.
Stack guard pages. Those are used to detect stack overflows, right?
Yeah. Right. And when you use larger data page sizes, it can sometimes limit the maximum number of threads you can create because of how the stack guard pages need to be aligned.
Okay, so larger pages can be beneficial in some cases, but we need to be aware of these potential drawbacks. Now, what about variable large page size support, or VLPSS? What is that all about?
Right, so VLPSS, it's a more advanced memory management feature that takes advantage of some hardware capabilities on IBM power systems.
What does it do?
Basically, it lets you use these 16 millibit mixed pages. These pages can be managed by the operating system at either a 4 KB or 64 KB granularity.
But they're still treated as 16 millibit pages by the hardware.
Exactly. So applications can still benefit from those large 16 millibit hardware page translations, which can really boost performance.
Sounds powerful. Are there any special requirements for using VLPSS?
Yeah, you need the right hardware, of course. You also need root authority to configure it. Plus, those 16 millibit user memory regions need to be fully resident in physical memory, meaning they can't be paged out. And you need at least 16 gigabits of RAM to use it.
Okay, so VLPSS is really geared towards those high-performance computing environments with lots of memory.
Yeah.
Now, whether we're configuring page sizes directly or using something like VLPSS, what are some general things we should keep in mind about memory usage when we're dealing with larger page sizes?
It's really important to carefully analyze how your applications are using memory. You want to make sure that using larger pages isn't going to increase memory fragmentation.
Right, and we can use tools like say vmon and vmstat to monitor memory usage and see if that's happening.
Exactly. And generally speaking, it's a good idea to stick with the default page sizes unless